Let's start from the Hamiltonian in classical physics. For a system of particles, we can write down the Hamiltonian in the following fashion. We have the dot product between momentum and the vector x dot minus the Lagrangian. Now, let's also write down Euler-Lagrange equations. In particular, we have the derivative with respect to time, the total derivative. Then we have the partial derivative of the Lagrangian with respect to x dot. And this quantity here is also equal to momentum p minus the derivative of the Lagrangian with respect to x equal to 0, the 0 vector if you want. The Hamiltonian can be thought of as a function of the variables x and p, whereas the Lagrangian can be thought of as a function of x, x dot, and t. So basically, this means that from the definition of the Hamiltonian, we have the gradient of the Hamiltonian with respect to momentum is equal to x dot, because the Lagrangian is independent of momentum. The Lagrangian depends on x dot, so we are treating them to be as if they are independent. And the time derivative of momentum from here is equal to the time derivative of this, which is equal to this. So we have dl over dx, and this is equal to minus the derivative of the Hamiltonian with respect to x, as you can see from here, because these quantities are independent of x. These are also known as Hamilton equations. Now, if we consider a generic function f, which depends on x, p, and t, and we take the total derivative with respect to time, this is equal to the partial derivative of f with respect to t, if it depends on time explicitly. Then we also have the gradient with respect to x, so basically this is a d over dx vector, the gradient of f, and then we have the dot product with x dot, plus the gradient of f with respect to p, and by this I mean d over dp dot product with p dot. But at this point we can substitute this expression here for p dot and this expression here for x dot in here. So we can rewrite this in the following fashion. We have df over dt plus gradient with respect to x of f dot product gradient with respect to p of h minus gradient with respect to x of h dot product gradient with respect to p of f. Now this quantity here can also be rewritten if you want with the summation over I or over any index. I'm going to label it as I. We have a df over dxi dh over dpi minus dh over dxi df over dpi, and this is defined as the so-called Poisson bracket, and it's labeled like this: curly bracket f h curly bracket, so like this. So this is a definition if you want, and therefore this can be written as df over dt plus Poisson bracket of fh. Now there is an analogy with the quantum mechanics, in particular with the Heisenberg equation. If you replace the Poisson bracket with the commutator, but I will not get into these details, but actually you can, let's say, you can find a way to pass from classical mechanics to quantum mechanics by switching from the Poisson bracket to the commutator. And in physics this is quite interesting, but this is not the video where I'm going to discuss that. But anyway, there are also other important analogies with quantum mechanics, and I will not touch upon the physics. I will show you the mathematics. In particular, if you take the Poisson bracket between Pi and Pj, so you use the definition there and you treat Pi and Pj as independent variables, so they are independent if they are different, if I is different from j. And also remember that P is independent of x. You can show that this is equal to 0 quite easily, as well as the following one, the Poisson bracket between xi and xj. And quite easily you can also show that xi and pj, in particular its Poisson bracket, is equal to delta ij, which is equal to the minus the Poisson bracket of pi xj. And basically this is already something, this is something similar to what you have in quantum physics. If you replace the Poisson bracket with a commutator and then you multiply by the imaginary unit and h bar, it's related to the Heisenberg uncertainty principle, if you know what it is and if you think about it. But I'm not going to say anything more than that. And another important Poisson bracket is the following one. And now let me also define angular momentum. In particular, Lj is equal to the Levi-Civita symbol, epsilon j I k, xi and pk, and here you have to sum over I and over k, so that summation is implicit. This is the Levi-Civita symbol, which is equal to 1 for positive permutations of j I k. So it's 0 if two of these indices are equal, or even if all of them are equal. And it can only be non-zero if they are all different. So they can be either, they can be 1, 2, 3 in different orders. And there is a sign that you consider when you consider the permutation of 1, 2, and 3. So if you have epsilon 1, 2, 3, you define this to be positive and it is equal to plus 1. And then for negative permutations, for example, epsilon 2, 1, 3, it is a negative permutation because in order to get 1, 2, 3, you have to swap 2 and 1 only one time. So you have 1, 2, 3. So after you swap these two, you make one swap and then you obtain the positive permutation, so you will get a minus 1 here. And so if you have to swap these numbers an odd number of times to get 1, 2, 3, you're going to get, of course, minus 1. But this is just a definition of the Levi-Civita symbol, which you can find everywhere, basically. So I'm not going to discuss it any further. Now, we can calculate the Poisson bracket between Pi and Lj. Now, this is a little bit more interesting, so let's do it. So you have to sum over some integer that I'm going to call m. It's quite easy to see that you will get 0 when you consider this part of the Poisson bracket, because you have to take the derivative of p with respect to x. So you have the derivative of pi with respect to xm, and that's 0 for every integer I and every integer m. And then you have minus the derivative, you have the derivative. So let me update my screen. The derivative of Lj with respect to xm multiplied by the derivative of pi with respect to pm. Now this derivative here is the Kronecker delta Im. So basically this calculation will simply give you minus the derivative of Lj with respect to xi, which is equal to minus epsilon j I k pk which is equal to epsilon I j k pk. If you just swap j and I, you will get a minus 1, so you can cancel this minus. And similarly, you can also calculate the Poisson bracket between Li and Lj. And incredibly, all these Poisson brackets are very, very close to commutators. As I said, you just have to make a substitution. So you replace the Poisson bracket with the commutator. So here in this case you have operators. These are operators, and then you have I h bar, and then here you have the classical result where you replace scalars with commutators. But I will not write down the result for quantum mechanics here. So I want to calculate this Poisson bracket. These Poisson brackets, by the way, are also important to study the dynamics of a system. They are just a different way to study the dynamics of a classical system. Now, this is quite, I mean, it's a little bit more complicated, but with some work it can be calculated. You have to sum over m. Now, when you take the derivatives and you consider the definition of angular momentum written in this form, and with the proper relabeling of these dummy indices, because you have to sum over them. And if you want, I could also avoid writing down this summation, as long as I remember the fact that when I see a repeated index, I have to sum over it. Now, for now, let me just write down the summation over m, but there are also some other summations that are implicit when you see other repeated indices. So it's some kind of mixed notation that is not so good, but uh, as long as we understand each other, it's fine. So we sum over m, and then I have epsilon I lk, so I have relabeled some indices there, delta ml, which comes from taking a certain derivative, pk, and then I have epsilon jsh x, let me write it properly, x s delta mh plus, then I have minus epsilon ilk, then I have another epsilon, but first let me write xl delta km times epsilon jsh delta sm ph. Now we can also rewrite this in the following fashion. We sum over m. We have epsilon imk epsilon jsm xs pk minus epsilon ilm epsilon jm h xl ph. And then I'm going to use a formula for a product of Levi-Civita symbols with one index in common. So we have the same index and we are summing over that index. There is a formula for that. I will not get into the details of the formula. It's not complicated. I've also explained it in other videos, in certain courses. But I mean, it's not difficult to work out. In particular, we get a product of Kronecker deltas of the kind. So we get a minus delta ij delta ks minus delta is delta kj. So this result comes from taking the sum of this part, the sum of this product of Levi-Civita symbols. Then I have xs pk, and then I have this minus product, minus the product of these Levi-Civita symbols, and the sum of that can be rewritten in a similar fashion. So we have minus minus, which gives me a plus, delta ij delta lh minus delta ih delta lj xlph. Now, I mean, you can verify that this formula is correct, but I will not I will not will not give you more comments than this. Now this will give us minus delta ij, and this delta ks multiplied by xs pk will give me the dot product between the vector x and p plus xi pj. When you multiply these two deltas with this is what you get. Then we get plus delta ij x dot p, and this will cancel this, minus xj pi. So the result is xi pj minus xj pi. And we can show quite easily that this is equal to epsilon ijk, and then we have lk. So we have to sum over k here. It's quite easy to show because we have epsilon ijk, and then the formula for lk is epsilon k, and then we have other indices, and we have to be careful not to use the same indices as this. For example, s and l, xs and pl. And now we can use the formula for the product of Levi-Civita symbols. In this case, we are summing over k. It's a repeated index, and we have delta is delta jl minus delta il delta js multiplied by xspl, and this gives us xi pj minus xj pi, like that. And it's basically equal to this. So we have shown that this Poisson bracket is equal to this. And there is an enormous amount of similarity between this formula and a similar one that you can see in quantum mechanics if you study quantum mechanics, for example. So this part of physics is not, let's say, studied or analyzed so often because I mean it's quite advanced, but that's not the point. The point is that one does not come across very often with Poisson brackets, because there are other ways to tackle physics problems, and it's not mandatory to use Poisson brackets. But the formalism of Poisson brackets can be very useful when you study quantum mechanics, or if you study some advanced concepts related to the motion of rigid bodies, or in general the motion of classical systems.